right now. That's specified by some function which we call a transition probability function, probability that j given z comma z. And this is a very classical list. Goes back to a long way, 60s or in 50s, and it's used extensively in communications, control operations, finance, robotics. So we'll consider there are several different types of course, I mentioned control process. So you're controlling this, you're sort of influencing this probability at each time. So there should be some purpose, some performance measure which you are trying to optimize. There are several traditional performance measures from clusters. I have taken the simplest one here. It's called discounted cost. So beta is some parameter between 0 and 1, which in particular make sure that this one is well defined. There is some k of xm, zm is the cost you pay at time n m. That's the instantaneous cost, and you want to minimize the sum of the discounted cost for the infinite future. Typically, this kind of model is very popular when money is involved because naturally beta turns out to be 1 by 1 plus r, where r is the interest rate, because the money you spend today is more valuable than the same amount you spend tomorrow. Okay, so this is again all standard. This may be boring for people who already know this, but it will work with anyway. So you define what's called a value function or cost to go function, the minimum cost to go. So that if you are currently at state I, you look into the infinite future and define the minimum cost over all possible choices of your control. Call that V of I. So it depends only on where you are right now. And then this satisfies the dynamic programming principle, which is the verbal statement is the minimum cost to go from now on is the minimum of what I pay immediately plus minimum cost to go from next stage on, which of course intuitively makes sense. So here, because it's discounted cost, I have to slightly modify this. I have the minimum discounted cost to go from next stage on, and that leads to this equation for V. So V of I is minimum. So this is the minimum cost to go from I. If you are in I at present moment, minimum over your current control choice of the immediate cost plus discounted average cost, because you don't know exactly where you are landing up. So you have to take the conditional average of Vj is the cost from if you land up in J, and average out with respect to your probability function. And this, of course, also both depend on your control choice. So the immediate cost also depends on your control, and the transition probability also depends on your control, and you minimize the control variable. So what it does is to reduce this. You are minimizing over this infinite sequence of random variables, Z1, Z2, etc. It's reduced to a one-step optimization. So if I know V, if I am in state I, just minimize this and pick that as my control. So for the later use, I'll define this quantity Q. Q I comma U is simply what happens in the square bracket. So this is just saying nothing. I'm just giving this a name. So KIU plus beta times some PJ given I U BJ, I call QI comma U. Then if I minimize this Q and find V of I, then as I said, that's the optimal what's called stationary Markov policy. So Zn as the function of the current state, V of xn will be optimal. And I'll explain these words. So stationary because there's no explicit dependence on time. Zn was V of n comma xn, I wouldn't have got it stationary. But if you are in state I, you choose your control depending on I, not on when you arrive at I. If you are in I today or tomorrow, you make the same decision. It's Markov because it doesn't depend on the past. You just see where you are currently and use that. So you don't have to depend. You don't have to remember the time or how you arrived at xn. Once you are in xn, you choose your control to be this function of V, function V of xn, where V is given by this from that. Just this minimization gives you a choice of things. Okay, so that's sort of traditional dynamic programming approach to solving this kind of problems. And since I defined Q to be this entire object in square brackets, this depended only on I, Q depends on both. I could also write the Q dynamic programming equation. So of course all I have done is go back again. This is my definition of V, and Vi is minimum over U of QiU. So similarly, Vj is minimum over U prime of Qju prime. So if I just plug that in, I get an equation for Q instead of V. So just compare this and this. Compare this equation and this. The main difference is that here the minimum is outside, the averaging is inside. Here the averaging outside and minimum is inside. Of course, you have lost a bit here because now see the state dimension, the possible values of I are say m. That this is an m-dimensional vector V. This will be much larger because this is possible values of I and possible values of V. So much larger vector, but the averaging has been put outside. So anyway, either you solve the first equation for V or the equation for Q. Then just by minimizing, you know the optimal policy. So your objective, since you want to find the optimal policy, your objective would be to either solve the equation for V or equation for Q. So there are multiple schemes. One standard scheme is what's called value iteration. You just iterate. You start with some guess V0, plug it in on the right hand side, get V1, then plug V1, get V2, and just solve it recursively. So in the abstract, I can think of this equation. If I write this as a vector equation, V1, V2, dot, dot. So the form V equal to F of V. What I'm doing here is just do the iteration Vn plus 1 is F of Vn, starting with some arbitrary guess V0. And one can show that will convert to the correct V. Similarly, I can write an iteration for Q that would convert to the correct Q. Okay. So of course, as I said, I have increased that when going from V to Q, I have increased the dimensionality. So usually these problems, incidentally, this theory of dynamic programming for Markov decision process was developed by Richard Bellman, who also coined this phrase curse of dimensionality, because the size grows up very fast. In fact, and since I am in electrical engineering, I typically look for problems which involve Qs. So for example, if you have n Qs, so all of say same buffer size, it would go exponentially in n. In no time, even in problems which appear to be small and mild, the size of the problem becomes very fast. It becomes very large very fast. So I have made the problem worse by going from V to Q, but as I said, the advantage is that the averaging has come outside of the nonlinear. There's only one nonlinear operation, which is minimization, and it was outside in the original dynamic programming equation. Now I have pushed it inside, and that makes it accessible to what's called stochastic approximation. So this is the other technique I need. There are a few slides on that. Because this is called due to Herbert Robbins and his student J.P. Monroe, and goes back to 1951. So it's from these are statisticians. So the idea was that they want to solve the equation Hx equal to 0 given some noisy observation. So think of a black box. You give input x, it spits out Hx plus noise. Okay. So what they did was to make it recursive. So they iteratively try to solve this equation. So at time n you start with some guess x0. At time n you have xn, you feed it to the black box. It gives you xn plus noise. So this is my noise. So the important thing to note is that you do not know this and this separately. You only know the sum. If you could figure out hxn, all this was unnecessary. Okay, so you only know the sum. And the clever thing they did was to introduce this slowly decreasing step size. So this is an uncorrelated sequence. So the standard assumption is that conditional expectation given the path of prime n is 0. And what they did was to introduce this clever step size sequence. So sum of n is infinite and sum of n square is finite. So standard examples are 1 by n log n. So it's a slowly decreasing. If it decreases too fast, then this wouldn't be infinite. If it decreases too slow, this wouldn't be finite. So it has to sort of go to 0 at the correct rate. Okay, let me just mention one thing. So this gives the impression that one is stuck with additive noise model, which is not true. Most of the time you have situations like this, where there is some nonlinear function of xn, comma, some IID noise. But you can put it into the previous form simply by replacing, so define h of x as freeze x and just average out over psi. Psi is so these are zeta ends or IID. So take psi as basically with respect to the distribution of zeta ends. Call that hx, and then define mn plus 1 by this original object here minus hxn. So add and subtract h of xn, and this turns out to be the one-step conditional expectation of this. So it reduces to this form, where this is uncorrelated with the path because it's subtracted of the conditional expectation given the path. Okay, so this is seemingly restrictive, but it's not. It's very general. So, and this is usually the situation you are in. You are given some algorithm like equation like this, and what you do is just subtract of those function, add and subtract those things. Okay, so the original approach was sort of purely probabilistic, but this more successful approach developed by these people in Russia and extended extensively by Leonard in Sweden. It's based on the observation that you can think of it as a noisy discretization of the differential equation. It's not equal to hx. Okay. So if you look at this equation, if the noise was not there and n was constant, it would be xn plus 1 is xn plus a times hxn. So if I think of a as a small step, so it's just a Euler scheme. This is how you would implement a differential equation on a computer. So it's a standard numerical scheme for a differential equation is just take small time discretization and make it a discrete equation. So what's extra is that two things. One is that the noise, the step size is slowly decreasing, and there's noise. So it's a noisy discretization of the differential equation. And what one can show is that under suitable technical conditions, the algorithm with probability 1 will have the same asymptotic behavior as the differential equation. So if the differential equation has a unique, it's a nice sort of what's called asymptotically stable equilibrium star, then the algorithm converges there. So this is extremely useful because you can kind of go backwards. I mean, you have any convergent differential equation, there's a sort of potential algorithm for you. Just discrete, I mean, if you have a noisy measurement of the right hand side, you have an algorithm with some promise of convergence. Okay, so there are problems. Of course, I won't run into them in what I'm going to do, but I just want to warn you that in general there can be multiple equilibria, or there can be more general limit sets. The differential equation doesn't have to converge to an equilibrium, even if it is not going up. You can converge to a limit cycle or some strange attractors and so on. There are some saving graces. For example, one can show that if the noise is rich enough, it will avoid all unstable equilibria, probability 1. And many times in algorithmic situations, the undesired equilibria are, with good luck, also unstable, so you don't see that. That does happen sometimes. Then also you need a priori guarantee that it's not blowing up. This is not always easy to prove, but there are tests for that. And also, if it cannot prove it, there are standards or tweaks. So for example, you can take a very large set and project the algorithm back to that set if it wanders off too much and so on. Then this thing is actually relevant for what I'm doing, which is that many times for the kind of algorithm I'm going to look at, that typically asynchronous in the sense that different components of the vector are updated on different clocks. That leads to a lot of problems. So one has to be careful about that as well. Okay, so for example, the different components could be evaluated by different processors which are networked, and there's some pass messages to each other. Or for the learning algorithms, you often just use a single simulation run or actual real-time data, and anyway, you'll see how the asynchrony arises in this problem. Okay, so that was more or less the background. Any questions about this? So the two topics I need, one is the Markov-Decision process and stochastic. Okay, so the Q-learning algorithm, which I mentioned in the beginning of Watkins, what he did was the following. So suppose you have a simulation device which just suppose you don't have the transition mechanism C, probability P, or it often happens that it's just plain too complicated. Okay. So a typical situation is, for example, that is for people working in communications and so on, there is some large queuing network. Okay. in principle, each queue may be simple, something arrivals and goes and the arrival rate, departure rate. So, but once the whole thing is connected together, it's a massive Markov chain and it's a very complicated behavior. So, it may not be easy to keep track and calculate all the time, but it's often easy to simulate because you have a very large complicated system which you have put together by connecting fairly simple smaller objects which you can simulate and connect together. So for example, for network there are standard softwares which do that. So suppose you have a simulation device which can on demand give me a random variable psi iu sub n with this distribution. Okay. Then Watkins algorithm does this. So what if you compare that with the relative algorithm? So I have this condition average here. So what one does is to replace this, forget this average and just generate a random variable with this distribution and plug it in here. Okay. So instead of averaging, you plug in an actual random variable with the given distribution. But that becomes like a random walk. That's not a very stable thing. So what you do is, instead of putting this equal to that, put it equal to a converse combination of the previous Q, that is Qn, and the correction suggested by this. That's what I have. So this is the converse combination of the previous guess with a small, with a large weight and a small weight on the corrected thing. So here instead of the averaging, I have plugged in the random variable with the desired distribution. And as I said, usually you just have a long simulation run, which you run a single chain. For example, operate in a simulation of network, you would have a single chain running. So at time n, you observe current xn and you can choose current zn. And therefore, you update only that particular component. That's what makes it asynchronous. You update only one component at a time. So if I am in state I and I have choose action u, I will come update I, u component, the remaining I leave and plus. So this is what's called indicator function. This is 1 if xn is I, zn is u, and 0 otherwise. So if either xn is not I or zn is not u, this is 0, and this qn plus 1 is qn, you are not changing. If xn is I and zn is u, then you make this small correction based on the dynamic programming. And actually there's some tweak needed that you have to make sure that all pairs I, u are sampled sufficiently often, so you have to make sure that you need some small randomization to ensure an exploration of all state action. So this is of course a stochastic approximation algorithm. So you do the standard thing, it's not hard. So you just take one step conditional expression and just add and subtract it. That will convert this term. So this is the kind of random term on the right hand side, which involves new information. So add and subtract it one step conditional expression and put it in the standard form. It leads to this differential equation where f is in fact from the, if I move back all the way, think of this as if I string this out as a vector, as I and q variables over the z possible values, I can write this as qn plus 1 is fqn. Sorry, there's n missing, should have been superscript n. This equation, otherwise of the form q equal to f of q. Okay? So that's the f I'm interested in. You get this differential equation. And one can show that it has some nice properties which allow you to show that in fact it will converge to the solution of if q star equal to q star is the solution you want. So this differential equation has this nice convergence, and therefore the stochastic approximation, the Q learning algorithm converges. So this is basically the convergence proof for the Watkins algorithm. And there are several other costs. So as I said, that's why I picked discounted because relatively simple. The finite horizon cost, where actually you have to allow time dependence as well. It's got infinite time. So how much time is remaining also matters. Then there is a long run average cost which is popular in communications applications, which kind of steady state. We try to optimize over the possible state behaviors. This is hard to analyze. This is even harder, which is growth rate, exponential growth rate of some e raised to something. This in fact lead to what's called this kind of nonlinear eigenvalue problem. Both vi and lambda are unknown. And this is very popular with finance people, as you might guess, because it's compounding. They also, their models, they use geometric programming. So it naturally leads to this kind of problem. The original intention for introducing this exponential cost was people to objection to this kind of cost, saying that when you take expectation of something, this kind of takes, you're taking care of the average behavior, but there could be non-trivial fluctuations around it. So there's this joke about statisticians that they can stick their head in fire and feet in ice and say that they are all right on the average. So to take care of the issues of variance, people try to work with average plus some constant times variance, but that becomes messy. It's not easy to handle. So this was promoted by a statistician called Peter Whittle in Cambridge again. Because exponential, if you expand exponential into its series expansion, it in some ways captures all movements. In fact, typically you put some parameters, theta here, and you say that your risk averse if theta is positive, risk seeking if theta is negative, and theta tending to 0 is called risk neutral, corresponds to this problem. So that's something. What's that?
Previous.
Yes?
No, previous. The first one that. Yeah, this one, Q dot T. What would be the interpretation? Can you just explain?
So FQ is actually the dynamic programming operator. So my dynamic programming equation was the form Q equal to FQ.
No, I want a kind of a physical explanation, a kind of a scenario where does it fit.
So that depends on the problem. So this is, see for example, if I were looking at a queuing problem, since I work in those areas, I think about those examples. So for example, some communication problem, the cost, so it's a discounted sum of the infinite horizon cost. The cost is typically the average queue length plus some constant time, something on the power expected. That's one typical cost. So it would be total, so it's kind of tries to strike a balance between the two. This, for example, if you have a randomly varying channel and you are doing what's called opportunistic transmission. When the channel is good, you want to push as much as you can because it takes less power. When the channel is bad, you don't want to transmit, but then you are queuing up, so that there are delays. So the cost which I just mentioned captures this delay and power trade-off. So that's one example. But people in operations systems, for example, there is inventory. So how much you are, there's some cost you pay for storing the inventory and for reordering and so on. So there are analogous situations, but the framework is kind of general, used in several different. Robotics people use it for path planning and so on. But the reinforcement learning algorithms are quite popular with the robotics community, but I am less familiar with it. There's a book by Trun and somebody else called Probabilistic Robotics, which is a lot of things. Okay, so yeah, so that was more or less the background material. So I'll start with, so I'm going to think of, discuss a few different applications which are, I mean, the same technique but not the same problem, in the sense that this reinforcement learning, at least the part I have, that's a very wide area. The part which I described is reinforcement learning for approximate dynamic programming, which is motivated by this Markov decision process and their applications. What I want to say is that you can also use it for sort of linear algebra computations involving non-negative matrices. So I'm going to give several examples of that. So this is something called gossip algorithm. So this actually is called gossip now, but this model is very old. Due to again a statistician called Maurice Bigwood. So this is just a model for, it was published in fact in Journal of Psychological Research, so model of opinion formation. So xn plus 1 is how much is some vector indicating, so ith component tells you how person I values some commodity, say, okay. So the way he updates his opinion is just put some weight on his own previous opinion, looks at his friends, and takes some weighted average of his friends and takes a convex combination of two. So you update your opinion based on what your own belief is and what you hear from your neighbors. And Ej given I is the stochastic matrix. So one can of course interpret it as probability of going from I to J for a Markov chain, but here it's simply the weight. So this is the weight I puts on his what his neighbor J believes. So this the typo here, this should have been pi I. So suppose x0 is the initial opinion vector. So x0 I is the opinion of I at time, opinion of person I at time 0. This iteration will converge to sum of pi I x0 I, so with pi, where pi is what's called a stationary distribution. It's given by this linear system pi p equal to pi. So if you think of a random process which goes from I to j with probability pj given I, this is actually the distribution time tends to infinity. It would settle into an equilibrium distribution. That's what we call pi. Okay. And that's given by pi p equal to pi. This is also quite standard. And this gossip algorithm actually to start maybe exactly when this activity started, but it has been very active area of research for last 10-15 years, mainly because of computation on sensor network. This is of course a vanilla version where you just want to do pure averaging. So you have several nodes spread out geographically. Each node can listen to its neighbors, and what it does is so each one node measures something, say temperature, and you want the average temperature. So they just iteratively average over the neighbors, and asymptotically you will get the global average. So of course this is a weighted average, pi I, weighted by pi I, but you can arrange things so that pi I is actually 1 by L. If you want just the average with respect to, if you just want the arithmetic mean, and you can do that by choosing P as a what's called a doubly stochastic matrix. So with the stochastic matrix, the row sums are 1. If the column sums are also 1, then the stationary distribution is uniform. So this is of course fairly trivial exercise to show. So this is not a research problem. The research problem was how to do this very fast. Okay, so generally this convergence is dictated by the absolute value of the second largest eigenvalue of this matrix. And the problem was to design P so that the second largest, the absolute value of the second largest eigenvalue, the top eigenvalue is 1, corresponding to the left eigenvector pi. The second eigenvalue, let's call it lambda. So mod lambda is what will dictate the rate of convergence. How to minimize that? That was the problem which Stephen Boyd and his students did a lot of work on in Stanford. And then there's a book, I don't know if I referred to it or not. There's a book by Devrat Shah, who was a student there, but now he's at MIT. He did a lot more work. So this is not the only problem. There are problems how to calculate the maximum, or how to just simply broadcast one piece of data as fast as you can. There are a lot of problems of this level. So I'm taking the simple problem of averaging. Now the thing is that if you consider the stochastic version, you get into trouble already. Suppose, see for example, if you have a wireless medium, you cannot listen to all your neighbors at the same time. Okay, because not everybody can transmit at the same time. So what you would do is poll one neighbor, say at time n, you pick a neighbor psi n of I. So I picks a neighbor psi n of I, and takes the average of its own previous value and what the psi n I thinks. Okay. So this is a stochastic approximation again. Now the limiting ODE becomes x naught equal to t minus I h t. So this is, of course, the ODE is nice. It will converge to, in fact, it will converge to a vector which will be constant. It's a constant multiple of 1, 1, 1, 1. Okay. This is the problem is that it's marginally stable in the sense that one eigenvalue is 0. It's not. I mean, if you have done some control theory, I mean, if this linear differential equations are stable, if all eigenvalues are strictly on the left plane, if they're on the imaginary axis, then it's marginally stable. If even one eigenvalue goes to the right of the imaginary axis, it's stable. So this is marginally stable. What one can show is that for any initial condition, it will converge to some constant vector. But which constant vector it converges to will depend on where you start. Okay. Now I was interested in my problem was start with x0 and converge to the average of x0. which if I do this, run this differential equation, it will happen. If I start at x0, it will converge to the average of x0. But my system is not this, my system is this. So there's some noise. So what one can show is that one can prove that it will converge to a common value, but it may not be the one you want. So there are two problems here. There's also a lot of work on what's called the consensus problem. You want several agents to agree on something. So here you do get consensus. Okay, so everyone, so the vector xt will converge to some constant vector. So the limit is same. So xt of I will converge to some c independent of I. So all of them converge to a common value. But here I will, so you get consensus, but here I want more. I want them to convert to a specific value, namely sum of pi I x0 I. So you have to consider, so this is a different, so this does not work. The simple concept does not work. So I want to consider alternative algorithm. So think of this linear equation. One can show that this is called discrete Poisson equation. One can show that kappa actually, so this is both g and kappa are unknown. Kappa is in fact, you can show it's this particular thing which you want, and d is unique up to an additive constant. And this arises naturally in the average cost Markov decision process, and there's an existing algorithm for it. You just some simple iteration, you subtract off this offset, so fix some I0 and subtract off this offset so that it doesn't go. And there's a stochastic approximation version which leads to a ODE. And the interesting thing is that now it has this, it's not just v dot equal to p minus iv, you are also subtracting this quantity. Yeah, actually this is a scalar. I should have put a vector, constant vector of 1s multiplying this. But anyway, this is enough to stabilize it, and it will converge to v and I0 component which converges to what you want. So this is a almost distributed algorithm because everybody needs to know the I0. This one scalar you have to broadcast it somehow. Barring that, it will converge to the correct value. Okay. And there, of course, this is not the only possible choice of offset. There are other possible offsets which, for example, you can subtract off the average value also, which you can contribute, which you can compute it again in a distributed fashion separately, etc. That will sort of increase the size of the vector, but it can be done. So by doubling up the problem size, you can replace this by something else which is computable in a distributed fashion. So either use broadcast this or replace it by average which can be computed in distributed fashion. So there you use a doubly stochastic matrix. That's the kind of easier to do. Okay, so this is one problem. So the thing is that this I pulled out as though I pulled it out of nowhere, but it has history. So this actually is this nonlinear version of this. With if I put I comma u here and put a min outside, it becomes actually a dynamic programming equation for the average cost problem. And this is simply a reinforcement learning algorithm problem which we had studied long back in for average cost control, which allows you to, which you can sort of morph into an averaging scheme over networks. That was my first example. Second is for the ranking problem. So many of these ranking problems basically amount to finding the Perron-Frobenius eigenvector of a non-negative matrix Q. So for example, Google's PageRank is finding the stationary distribution. I will return to that because that can be treated separately. So that finds the top eigenvector of top left eigenvector of a stochastic matrix. There are other ways, for example, Kleinberg had this alternative ranking scheme for kids, so that calculates two ranks for hubs and authorities. So in a sense, hubs are kind of the nodes for, to which all other nodes take to look for information, and authorities are the sort of those from which things go out. So there are two different rankings, and those also amount to finding the top eigenvector of a non-negative matrix. In this case, this is the A transpose or A transpose A. The A is the adjacency matrix of the class. So anyway, so and there are others, like for example for reputation systems, some people have proposed something called eigentrust algorithm. And that there's a nice survey by a person called Sebastiano Villa on the web, which he keeps updating. It's an ongoing survey. It's called spectral ranking, which gives the history, which is quite old. It goes back to Kendall and Vivek, and several more recent applications of ranking schemes based on proper parent probability eigenvectors. So standard algorithm is what's called the power method. Usually it's Qn plus 1 is capital Q, Qn. Then you normalize, usually by putting norm Qn here, I have put a somewhat more general F. Okay. I am going to use Q sub I naught. So if I plug in Q sub I naught here, it just becomes a multiplicative analog of for the. Yeah, so this algorithm, essentially, I won't go into it. Essentially, you put replace plus by into and minus by divide, you will end up with this multiplicative counterpart of that scheme. Okay, so this is the deterministic algorithm. I want to give a stochastic approximation version of it so that you can just sample neighbors and iterate. Okay, it becomes this. Now binomial thinking behind it. So this, of course, this is synchronous version. I have not written the asynchronous, which will take a more early, but so, basically one knows how to do that. And then the limiting differential equation is just, this is a more complicated differential equation, but one can show that this actually converges to, it's a nonlinear equation. One can show that it converges to the desired around Frobenius eigenvector. Of course, eigenvectors is not specified uniquely, it's specified only up to a multiple, scalar multiple. So it goes to the eigenvector whose I naught element is actually the eigenvector. Because this quantity will convert to the eigenvector. So this is a general sort of, again, this is like, in fact, I should say linear, it's not linear, it's just uncontrolled. It's a counterpart of an algorithm for risk sensitive control, the reinforcement learning algorithm for risk sensitive control. So I am recycling what I already know, namely there's an algorithm for control, which where I just remove the control part and it becomes an algorithm for a matrix computation. Okay, so now this is what basically I have contributed to this model. So this is the PageRank, as I said, is again you are calculating a top eigenvector. So it's a special case of what I just said, but it has some extra structure which you can exploit to do something similar. So PageRank is based on this random web surfer model. So this is of course the vanilla version. I'm sure Google has a lot more tweaks which we don't know about. But the idea is that from some web page I, you look at other pages to which this web page points, and this constant was Google constant. This is something like 0.85. So the probability. So C by so page I points to Ni other pages. So Ni is the number of web pages to which I points. The probability C by Ni, it goes to one of them. Okay, and then you just repeat that. And there's also a chance that you just stop that search after some amount of searching and start afresh. So 1 minus C by n, so with probability 1 minus C by n, n is the number of all web pages. You initiate a new search with a random initial web page. So this is the random web search model. So you go to with probability C, you go to one of your successors with equal probability. So divided the probability C divided equally between them. So C by Ni for each neighbor. And 1 minus with probability 1 minus C by n, you go to one random web page and start a new search. So this is defines the stochastic matrix, and in fact this factor makes it very convenient. It becomes if I didn't have that and I only considered a Markov chain where you go from one web page to another, there's this problem of what's called dangling nodes, and there may be some web pages who find nowhere. So for a chain that amounts to an absorbing state, you just go there and get stuck. So this small probability of starting a fresh search makes the chain irreducible, and it has a unique stationary distribution. That's part of follows from standard Markov chain theory, and what PageRank does is to rank it according to those. Of course, there are other variants like personalized PageRank and so on, but basically the idea is to find some stationary distribution. Okay. So So suppose instead of, this is the left eigenvector, phi q equal to phi. Suppose the algorithm I had earlier was for right eigenvector, so I define G as q raised to t, sorry, q transpose, and in this case, actually, I have this transition matrix given by Pj given as 1 by Ni for if I point to J0 otherwise. So to make it into the right eigenvector problem, I consider P transpose, and then X is you just write the equation for that and you get this. Okay. So because of this particular form, that it was C times something plus 1 minus C by n times the matrix of all ones. Okay. So that structure, so there is a convex combination of two matrices, one of which is a sort of somewhat complicated transition matrix, but other is just a constant matrix, just everything is one by n. Okay, so using that fact, I can actually solve this, in principle solve for this eigenvector and get this expression. Now since I am interested in ranking, I will throw this out and look for this object. Again, there's a typo this you will see. Okay, so I want to solve this equation now. So what I am going to do now is there's some idea which is quite handy. Several things. So far what I was doing is that I wanted to generate random variables according to probability Pj given I. Okay. So I was running a Markov chain when the Markov chain at time n is in I, then the next state is obviously going to be with probability j given I. So what I did not mention it, but the problem that arises is that because of the asynchrony, I am updating only one component at a time. They are sampled according to the stationary distribution. So the right hand side of the differential equation gets weighted by the stationary distribution. Now there are ways of working around it, and sometimes it doesn't matter. So it depends on the problem. So depending on the problem, you somehow handle it. So I won't get into that. But the important thing to note is that it was the transition probability you are interested in. You are generating pair random variables. So say xn comma xn plus 1. Eventually the distribution is going to be a pair distribution, where distribution of xn plus 1 given xn is given by pj given I, but distribution of xn will be the stationary distribution. What if I want xn? See, I am interested only in the transition probabilities. In fact, the fact that xn gets distributed according to pi asymptotically is a nuisance usually, which you have to work around. So what I do instead here is generate pairs. I don't run a Markov chain. I just randomly sample according to, so just generate independent identically distributed pairs xn comma yn, where xn are ion uniform, but the distribution of yn given xn is the transition probability. Okay. And then I have this algorithm. Now this does the correct thing. So the thing is, this will be sampled according to the uniform distribution, so it will get weighted by 1 by n, and this condition on this will be given by j given I times the distribution of x, which is again 1 by n, and that leads to this desired linear differential equation, which is convergent. It's convergent because c is less than 1. See what I did as opposed to what I did earlier, the difference is that the Google matrix is of the form C times P plus 1 minus C times something nice, which is very simple to write. I use that fact to just manipulate the equation so that I have to worry about only C times P, because the other thing I have absorbed in my computation. Now once this C multiplying P, C is a constant less than 1. That makes it a substochastic matrix, and so the eigenvalue of P, if C was not there, again I would have the same problem of marginal stability. P transpose minus I would be a marginally stable, but now it's multiplied by a number less than 1, so it's stable. So this works fine. You get a convergence with probability 1. Okay, so of course I don't know whether Google will care for this, but the advantage here is that Google scheme assumes a certain probabilistic model, that you go from site I to one of its successors with equal probability. I don't have to assume that. Even if the probabilities are something else, the algorithm will learn them. So you can just, assuming you can sample from the data, there's xn comma y, so which occur together. Okay, so you can learn the probabilities as well. Okay, so these are the this module, the last part, and this actually this does the ranking problem I described, but the title has been changed because the referee objected to it. It has some pedestrian title now, which I have forgotten. We thought we could get away with this, but okay, that is some history. I mean, there's a book for those who are statistics or probability. There's a famous book, classic book called How to Gamble If You Must, by Vivek and Savage, which is a highly technical book, contrary to the title, about probability theory in general. Certain aspects of probability theory. So we had modeled this after that, but the referee took strong exceptions, so the title is changed. But it will appear in the special issue of selected topics in syllabus. Okay, so what was common in this methodology was I have been doing the same thing again and again, so in different ways. So start with a non-negative matrix. You can always pull out the row sums of non-negative matrix, write it as a product of a diagonal matrix with positive entries on the diagonal times a stochastic matrix. Okay. So you are first multiplying the non-negative matrix Q by some vector x, so Q times x. So I write Q as D times P times x, where P is stochastic, D is diagonal, and then replace P times x, which becomes a row-wise. Each term will correspond to an averaging with respect to a stochastic matrix. Replace that average by a sample, actual random variable generated according to that transition probability, and then we get incremental correction as in stochastic approximation. So stochastic approximation basically averages out the noise. So once you make it incremental, that takes care of the fact that you have taken out the average and plugged in the random variable, but the algorithm will see the average, does the average for you. So this is the thing which I've been applying to various schemes. Just right now.
Thank you, sir. Any questions?
So, basically, your model definitely takes care of that everything is centralized to computing. More precisely, I would say that the computing node has complete information about the state space, information about the states of all the other elements in the.
So you need only your neighboring element.
Yeah, but
so basically computation on a graph, you look at your neighboring element. In fact, delays can be allowed as long as they're bounded. Yeah.
So since you do not know at what time the information, state information from the distant elements will come, how do you take care of that?
No, that's so kind of standard. So in the distributed stochastic approximation, if you have delays, then there's an additional error term which also goes to zero. So it will affect the rate at which the errors will be higher, but the asymptotic convergence is not affected. You have to put some moment assumptions on the delays. In particular, the delays are bounded, there is no problem.
For example, if you have some bus arrival at some node, at some distant node, and that cannot be captured immediately. The error will be very large initial state. That will stabilize after a long time.
Yeah, so it will depend, it will be problem dependent. But see, what this decreasing step size is actually taking care of that. So if you consider the correspondence between, so as I said, you can think of this algorithm as a discretization of the differential equation. So I consider, suppose the way you think of it is T0 is 0, T1 is A1, T2 is A1 plus A2, T3 is A1 plus A2 plus A3 and so on. So I can think of this A1, A2, A3 as step sizes. So it's kind of mapping, it's a time scaling. You get the differential equation after time scaling. But it's because n is decreasing, the time scaling goes sort of like this typically. So if the interval of width capital T, say, if you slide it right on towards infinity on the actual time axis, it gets mapped to smaller and smaller time interval on the OD time. And originally the step size was this Robbins-Monroe scheme. The step size was used in order to kill the noise because it makes the future noise less and less. But it also kills the delays.
So coming back to the previous slide, so what is the time complexity required for the first two?
We just take some, adding the.
generate these stochastic matrices.
No, see, in the kind of thing that I look at, you usually choose the. Okay, so suppose you are given, but typically it will be small because you see, again, it depends on the graph. If it's I mean, one would typically use it in situations when the number of neighbors is not very large is small compared to the total nodes. So each row will have non-zero entry only for the neighbors.
From a computer science background, since the whole purpose of this methodology is to speed up the process of computing. So, since you're doing stochastic approximation, the analysis showed that asymptotically the noise would cancel out.
Yeah.
But are there any analyses that if I stop after some n in terms of that, what would be the error function?
Yeah, there are this sample complexity kind of results for stochastic approximation in general, not specifically this.
No, for this. So
I could just apply the off-the-shelf result. I have not done that, but there are results available. See, this is not actually, this won't speed up anything. This is mainly if you are in a distributed situation and noisy situation anyway, you would do this. If you have a centralized and exact information, there's no need to do this. If you have a noisy distributed situation anyway, then you would resort to
yeah, but the purpose of the approximation is to speed up the main calculation, right?
No, see, okay.
Initially,
two main problems are one is that you don't have the data at the same point, so you have to communicate across the network. So, and to handle that aspect and handle noise, these are the and delay resolution. So these are the main issues. So compared to sort of centralized, complete non-noisy situation, this will be much slower. But I'll tell you the kind of results available for stochastic approximation, because it's a noisy situation, you don't have. So you have this. So what you can say, the kind of results you have is that given two parameters epsilon and delta, it will tell you how many samples you need to be within epsilon with probability exceeding 1 minus delta. Yeah, that's the kind of thing.
I would like to thank all the speakers for their presentation. We definitely learned a lot from it. I would now request Professor Samresh Mishra to present the speakers with certificate, bouquet and memento. Now I would like to call upon Professor N. Raja sir to give away the book. We will now proceed towards the tea break. Please be back in 15 minutes. Thank you.